let's talk about the time dependent perturbation theory. So, before we do that, let me tell you that in the time independent perturbation theory, the states of our system remained stationary, right? That is to say that they did not change with respect to time, because the Hamiltonian in that theory was not time dependent. Well, however, we may encounter systems, quantum systems, where the Hamiltonian may have this time dependence in it, and so we'll call those the time dependent Hamiltonians. And what we see is there's something funny happens, that there is a transition between the states that may occur, right? So think of like an electron that might make a transition from one energy level to another energy level. Well, this transition is very important for us then to study, and therefore we'll talk about something called the transition probability. And the transition probability is going to be extremely useful, or say fundamental, for the time dependent perturbation theory, right? Okay, so I'll write it down over here that we are going to be talking about from now on the transition probability, right? So I'll write like this. Okay, so to get an idea, we'll take a model, or we'll picture a model. A model goes something like this, that imagine that there is a quantum system that is initially in some state I, right? And then we turn on the perturbation, that is, we turn on the Hamiltonian, that is H1, as a function of time now, right? So we do this at t is equal to 0, and when we do that, the initial state of the system evolves into a final state of a system at some later time t, right? Okay, so to get even a more clearer idea, think of a hydrogen atom. Now the hydrogen atom, say it's initially in a state that is the 1s state, right? So this is the initial state of our hydrogen atom. Well, what can we do to change that? Let's shine a laser beam on it, right? So when we do that, the system or the hydrogen atom will evolve, or there will be a transition, right, of an electron from one state to another. It may excite, right? So then it will be called the excited state, and say that it excites to some state, say the final state is now 3p, right? Okay, so well, this initial state was 1s and the final state is 3p, right? So what is the probability that the hydrogen atom will go in a state 3p, right? Because it could have gone in any other state, but say that for specifically it goes into this state 3p, what was the probability that it would do that, right? So to solve this, first we shall look at our Schrödinger equation for the time evolution of a quantum system. So we have a quantum system and it evolves with time, right? So the Schrödinger equation for such a system is then the Hamiltonian acting on state psi is equal to iota h bar time derivative of my state psi, right? But now the Hamiltonian h is time dependent, So therefore we can write our H as the sum of the unperturbed Hamiltonian and the time dependent perturbed Hamiltonian. Okay, well, now there's a problem and let's discuss that. Okay, so the Hamiltonian is continuously changing because at every instant of time the Hamiltonian is going to change, right? Because it's dependent on time. So the problem is that now to find new eigenenergies, we will have to rediagonalize our Hamiltonian, right? Every time it changes, we'll have to rediagonalize it. But that is not possible, right? Because you see, it's going to change at every single instant of time and we'll have to rediagonalize it at every single instant of that time. So that's impossible, right? So now, instead of finding out the eigenenergies of the states, right, we would be rather interested in to see how this perturbation changes the time evolution of the system. So how does the system evolves under some perturbation? Okay, so we are going to use original energy eigenbases to expand the general states of our system, right? Even though these will not be the states eigenbases for the system, but we can use these, right, to expand the general states of the system. So let's see that before we turn on the perturbation of our system, before we perturb our system, we have our psi at t is equal to 0 is this thing over here. So it is the expansion coefficients on my state n, right? So these expansion coefficients are actually going to play a very, very important role in what we are going to do now, okay? And you will see that. So now without any perturbation, right? So without any perturbation, let's see what will be the time evolution, right? So let's write it down, okay? My psi, when my h1 is equal to 0, so this thing over here tells me that the perturbation is off at some time t is like this, the expansion coefficients Cn exponential of my negative iota over h bar En t. And what is evolving? My state n, right? My state n is evolving in time. So this is how we write the time evolution of a state psi when there is no perturbation, right? So this is how we write it, and we know this, right? Okay, so now let's include this time dependence in it, right? So now for the time dependence, we shall include a factor that shall reflect this time dependence, right? So there should be something that reflects the time dependence or tells us that there is some time dependence in our system, and that is what we are going to do with our expansion coefficients now. And we're going to allow that these expansion coefficients change with respect to time. So my Cn is now going to be my Cn as a function of time. So at every instant of time, these coefficients will change. Right, let's then now with this thing, I'll write down my state psi. And this time I'll write it down when the perturbation is on, right? So my h1 will not be equal to 0. So let's write this over here. So it's then going to be my sum over, I forgot to put the equal sign. Okay, sum over my n, Cn as a function of time, exponential negative iota over h cut or h bar En t, right? All of this acting on my n, state n. All right, initial state. So now let's see how will my Cn of t, or the expansion coefficient, this thing over here, will evolve, right? Or will have this time dependence on it. So before we do that, let me just mention over here that my Cn at my t is equal to 0 will simply be my Cn at 0. So here, this is when there is no perturbation, right? So this is for no perturbation. Right. Okay. Now let's move on and see how we'll write this Schrodinger equation now for the time evolved state. And now here there is going to be a lot of mathematics and algebra. So yeah, just a fair good warning over there. So let's write it down. We have H naught, or unperturbed Hamiltonian, plus the time dependent perturbed Hamiltonian that acts on my state psi, that is a function of time now, is equal to my iota over h cut, the time derivative of my state psi of t. Okay, but we just said that our state psi of t is summation n Cn of t exponential negative iota over h cut En t and state n, right? So it's this thing over here, right? We just said that our psi of t, when there is perturbation, it's this thing, right? Okay, so let's just then substitute this, and so I'll have my h. Okay, now I'll have to save some space and be careful with that. H plus h1 of t, right? So I'm doing this in this equation over here, right? In this one. Summation over all n Cn of t exponential, all I'm doing is putting the value of this psi, right? So exponential, just said I'll save space, exponential negative iota over h bar En times t, right, on my state n, right? All of this will be equal to, now I'm gonna have problem with space, okay, iota over h bar, the time derivative, right? Now all I have to do is open this psi. Okay, so what's that? That's then my sum over n, all n, Cn as a function of time, and this exponential thing over here, right? I don't know if I'll be able to write it clearly, but negative iota over h cut Et and and on n, right? So this n is with this exponential thing, right? It's outside the exponential, but it's with this. So what this is what we have now. Okay, but let's recall. I hope you don't get tired of what I'm going to recall now. The h not acting on my n gives me a constant energy eigenvalue and n, right? So I've used this a lot of times. This is for when we have no perturbation, right? Perturbation is turned off. So this is the unperturbed Hamiltonian. And what I'm going to do is I'm going to use this thing and I will substitute this in this equation that I wrote over here, right? This one. So yeah, let's go ahead and do this, right? Okay. So when I do that, what do I get? I will get sum over n of all my en cn as a function of time. I'll have my exponential negative iota e t over h cut over h bar. Just write clearly. Yeah. Right, and I'll have my state n plus my perturbed Hamiltonian as a function of time, right? I'll have my Cn as a function of time, and I'll have my exponential and my state n, right? So again, exponential negative iota e t over h bar and my state n. So I'll have this sum over here being equal to now iota h bar. Before I write this, let me just remind you again that all I'm doing is I'm putting that eigenvalue equation in this, that when my h acts on my psi, it gives me e and state psi back, right? So I'm just putting that thing in this last equation that I have written over here. Okay, let's go back. Okay, so I'll have all of this will be then equal to my iota h bar sum over my n's, and I'll have my time derivative of my Cn of t, right? And then I'll have my exponential negative iota over h bar e t, and I'll have my state n minus iota en. I'll save space 1 second. I had n here, minus iota en, and note that this n I have been writing it's with subscript n everywhere for now, right? Everywhere I have used e, it's with subscript n. Okay, so my iota en over h bar, Cn as a function of time, exponential negative iota over h bar et, and my state n. Let's close the brackets over here, and this will then be multiplied by, so there is a multiplication over here, right, with sum n my h, the perturbed Hamiltonian time dependent Cn of t exponential negative iota over h bar et and my state n. Okay, so now this thing, all of this will then be equal to iota h bar sum over n dt cn of t exponential, I'll just write it as this now, exponential of my negative iota over h bar et on my state state n. Ooh, okay, so this is what we have now, right? And so let's go on to the next page. And to simplify everything that we have done over here and to just see that what the left hand side and the right hand side of the equality sign is. So let's go here and I'll write it down over here. So what we have from all of that is now my sum over n, the perturbed Hamiltonian that is time dependent, my Cn expansion coefficients that are time dependent, times the exponential of negative iota over h bar e t. Okay, all of this on state n being equal to the iota h bar sum over n, the time derivative of my expansion coefficient Cn that depend on time, and e exponential negative iota over h bar et and my state psi n. Okay, now what we have to do is, because we are talking about the transition, right? So let's say that our system makes a transition into some arbitrary state k. Okay, let's call that state k. And now to proceed from here, what we will do is we'll take this equation, all of this, and we will project it onto that state k. So how do we do that? Well, it's very simple. Actually, let me just write, or I'll write it down, write all of this thing all over again. Okay, so projecting it onto state k is just by using the bra over here, k sum n h1 t cn as a function of time, exponential, all of the other things are the same as over here, right? Okay, negative iota over h bar et and my ket n, right? So save space being equal to, I'll have my k over here and then again all of this, right? So iota h bar sum over n time derivative of my expansion coefficients times my exponential negative iota over h bar e t and my state n. Okay, so when we do this, right, then all of this thing over here will be equal to, note that this e over here is my just a constant value, right? So I can take these quantities outside, right, of my inner product or the matrix element that's going to become, but my h is my Hamiltonian, which is not a constant value but an operator, so that will stay in. So then all of this thing over here will go on to become sum over n. I can take this outside. I can take Cn outside as a function of time. I can take my exponential outside, iota over h bar et, right? And I'll have now my k h prime or h1 of t, that is the perturbed Hamiltonian that depends on time, and I'll have my state n over here, just like that, right? And on the right hand side, what I will have is that using the orthogonality condition, we are going to use the orthogonality now from here, and what this quantity over here will become is, we can write it down now as iota h bar dt of my ck of t, not n but subscript k of t, right? And my exponential negative iota over h bar e k times t, right? It's not en anymore. Over here it was en. Let me just write it properly. Yeah, it was en over there, but now using the orthogonality and simplifying this thing, it has become ek, right? And so for cn of t has become ck of t, right? Because of the projection, right? Now let's just use this equation over here, move some terms, right, and write it in terms of, or in the form of, a differential equation, right? So what will that be? That will be simply my iota h bar, this thing over here, dt or d time derivative of my ck of t, right? All of this being equal to sum over my n's c t, my exponential, write it down like this, iota over h bar, okay, and I'll have my ek minus en. So this is the difference of energy times t, and what I'll be left with here is then this matrix element of my perturbed Hamiltonian, right? I hope you can see that, right? Okay, so this equation that I have written over here, it gives me a set of coupled differential equations, right? And they are pretty difficult to solve. So what we are going to do is, we are going to seek a perturbative solution, right? And we will expand our Cn expansion coefficients, so called, then in a perturbation series, right? So let's move on to the next page and write that down. So that perturbation series, now I write it down as my Cn is equal to Cn0 plus Cn1 plus Cn2 plus up to, well, so on, right? Okay, so now when there is no perturbation, right, then the differential equation that I wrote before, the zeroth order term, well, that becomes simply iota h bar time derivative ck0 as a function of time being equal to 0, right? This equation is just coming from this thing over here, right? This equation over here. Okay, so, well, The first order term, however, can be written as this thing, iota h bar dt, and now it's the first order term, so c1 k as a function of time t, so this being equal to sum n. Now cn of 0, I'll have the previous term, right? So whatever order I am computing on this cn, I'll have the previous order, right? So 0th order. Okay, so it's a function of time, of course, and exponential negative iota over h bar e k minus e n, right, multiplied by the t time, and I'll have my matrix element k, matrix element of my perturbed Hamiltonian, that is this. Now I did not write as a function of t here, but remember that this perturbed Hamiltonian is time dependent, right? Okay, now I'm going to use this equation later, so what I'm going to do is I'm going to call this equation over here, I'm going to say that this is my equation star, right? So equation star. Okay, let's move on further and say now that our system, assume that the system, okay, it starts in one particular eigenstate, right? And say that that eigenstate is my state I, right, initially, of a 0th order Hamiltonian, right? So that just means that it's unperturbed, right? So the Hamiltonian is unperturbed. So then that is to say that this is equal to my psi at t is equal to 0. So this is right. Okay, and so the initial coefficients will then obey this relation over here, that Cn of 0 is equal to delta n I. Okay, so now let's recall again that differential equation that I wrote previously for my unperturbed states, or that is 0th order, so it's this thing over here I just wrote previously, is equal to 0. And so this thing implies that my Cn 0 as a function of t time is then equal to my delta ni, right? Now let's take this Cn of 0 of t, right, and we are going to use this and put this in our equation star, this equation over here, right? And then this equation, the sum collapses, right? So it collapses the sum to just one term. So that's the reason of doing all of this thing that I have written over here, right? So we just need to collapse the sum to just one term, right? And so when I do that, what I have is that equation star now becomes iota h bar, the time derivative of my ck as a function of time is equal to my exponential, right, iota over h bar ek minus e n times t in exponential, and then the matrix element of my perturbed Hamiltonian, right, that depends on time, and I'll have my I over here now. Okay, so I have just used these relations, right? Okay, so now let's integrate this equation that I have just written over here, and upon the integration with respect to time, what do I get? I can then find my coefficient ck as a function of time being equal to 1 over iota h bar, right? This thing goes over there. So, and I have my integral 0 to t, my k, get basically again my matrix element of my perturbed time dependent Hamiltonian iota, I'm sorry, not iota, I over here, and exponential iota over h bar ek minus ei times t, but let's just write it as t prime because my integration limit is from 0 to t, right? So let's use this as a dummy variable t prime, and with respect to dt prime again. Okay, so this equation you can see over here is very important indeed, right? Because using this equation we can compute the expansion coefficients we have. So this equation basically tells us that how many expansion coefficients evolves, how the expansion coefficients evolves with time, right? So you can see over here, right? It's a function of time, and it's telling you, the equation is telling you how your expansion coefficient is going to evolve with time, subject to obviously some perturbation, that is over here h1 of t, right? Given that the system obviously started at some initial state I. Okay, now if you look at this equation, right, it has the form of a Fourier transform, right? So let's rewrite it. See, ck of t is equal to 1 over iota h bar time integral 0 to t k, the matrix element basically of my perturbed time dependent Hamiltonian I, exponential iota over h bar ek minus ei, now ek minus ei t prime dt prime, right? So let's close this over here. I'm sorry, dt prime again, obviously because it's a dummy variable, right? Let me box this equation, right? And I'm going to call that this equation is my equation lambda, right? So now we may say, right, that this is the Fourier, this ck of t, right, is a Fourier coefficient, right, in my frequency space, obviously, of the perturbation h1 of t at some Bohr frequency, right? So what is the Bohr frequency? The Bohr's frequency is omega ki, right, is equal to, because it's going from I to k, so this is like a transition, so it is ek minus ei over h bar, right? So it's you can see it is in this thing over here, right? So yeah, like I said previously, once again, that this is then the Fourier coefficient in the frequency space of my perturbation h1 of t, right, at this Bohr's frequency. So BOHR, Bohr's frequency. Right. Okay. So, well, now if you see, note that if your perturbed time dependent Hamiltonian has an appreciable amount of component at a Bohr frequency omega ki, say, associated with the difference in the energies delta E or Ek minus Ei between my state I to some state K, right? So it's going from my initial state to some another state, that is state K. Then of course the probability of the system to make that transition in the final state, right, is going to be large, right? Very, very large. Okay, so now that we have that out of the way, now we are almost done, right? So to find the probability that the system is measured to be in a particular final state, say state F at a later time t, right, we are going to project the time evolved state onto the final state F, right? Okay, so let's just do that over here. Let me get rid of this thing. Okay, so now what I want to do is find the probability that the state system is to be measured in a particular final state from some initial state. So let's write that down as probability of from my initial to final as a function of time. This is going to be equal to my state F, state psi, basically the time dependent state, evolved state projected onto the final state, right, and the square of this. That's my probability. So let's open this and write it down as F. Now my state psi of t was my sum n, Cn is a function of time, exponential negative iota over h bar En t, and my state n squared, right? Okay, so this over here is just my state psi of t, right? And then this whole thing inside the square, right, this thing over here, right, is simply equal to the CF expansion coefficient as a function of time, right? And then we have the modulus square outside. So, well, if it is equal to my expansion coefficient as a function of time, I have my expansion coefficients over here as a function of time defined. So all I'll have to do now is put in this value of Ck as a function of time and square that, and so I'll get the probability of my system making a transition from an initial state I to a final state F. So I'll write it down, right? So let's write that down. So it is the probability of my system from initial state to my final state F is going to be my 1 over h bar squared, and let me have this thing over here. So now all I'm doing is I'll go back, I'm putting the value of Ck of t, right, in this. Okay, so we have the time integral 0 to t f h1 as a function of t, get I exponential iota over h bar ef minus ei times t, right? And again, let's call this t prime, right? Close the brackets over here, exponential, and I have dt prime, right? And of course, not to forget my squared, this thing is squared. Okay, so this equation over here, or yeah, this equation over here is what gives me the probability of my system to be measured in a particular final state f from an initial state I in some time t. So this was it for the video, and this is the transition probability. This quantity over here, this is what we call our transition probability, right? And this is extremely useful to compute our transition amplitudes and things so on. So we also look at the transition rates, something we call transition rates, and we will do that in a later video. For this video, this is it, and I hope you enjoyed and you learned something new, right? So I'm going to end this video here.